Welcome to today's paper reading. Today's paper is titled, Design2Code, How Far Are We from Automating Front-End Engineering? This paper was published on the AR14 preprint by Chenglei C. and colleagues from Stanford University and Georgia Tech. The abstract highlights recent advancements in generative AI, particularly in multimodal understanding and code generation, which are enabling new approaches to front-end development. This paper introduces the Design2Code task, which involves converting visual designs into code implementations. To evaluate this, the authors curated a benchmark of 484 diverse real-world web pages and developed automatic evaluation metrics complemented by human evaluations. The study found that GPT-4v performs the best on this task, with generated web pages matching the visual appearance and content of the original in 49% of cases, and being considered better in 64% of cases. The analysis also reveals areas where open-source models can improve, such as visual element recall and layout design. The task of implementing visual designs of websites into functional code is challenging due to the need for sophisticated skills in understanding visual elements and translating them into structured code. This complexity has prevented many non-experts from building their own web applications. Additionally, the requirement for domain expertise complicates the web development process, necessitating collaboration among individuals with diverse skill sets. Recent advancements in code generation from natural language have not significantly addressed the challenges of generating code from user interface designs, which face issues such as diversity in visual and text signals. The Design2Code task aims to address these challenges by using multimodal large language models to translate user interface designs into functional code, thereby automating front-end engineering. Figure 1 illustrates the difference between the website dataset and our new Design2Code benchmark. The first row shows examples from the website dataset, which uses synthetically generated web pages for scalability. The last two rows display examples from our Design2Code benchmark, which employs real-world web pages to ensure they are realistic and diverse. This approach guarantees a wide range of complexities and a variety of real-world use cases, making the Design2Code benchmark more challenging and comprehensive. The Design2Code benchmark involves curating a dataset of 127.9K web pages, which are then filtered to 484 high-quality examples through automatic and manual processes. The dataset statistics show an average of 31,216 tokens per file, 158 tags, and a DOM depth of 13. For evaluation, the benchmark uses clip embedding similarity and a suite of element matching metrics to assess the accuracy of generated web pages, focusing on text, position, and color similarities. Table 1 compares the statistics of the website dataset with our new Design2Code benchmark. The Design2Code benchmark includes 484 test examples, each with an average length of 31,216 tokens and an average tag count of 158. These examples are significantly more complex and diverse, as indicated by the larger standard deviations in comparison to the website dataset. Figure 2 presents a pie chart illustrating the main topics of the web pages included in the Design2Code benchmark. The chart highlights that the most prominent domains are websites of companies or organizations, personal blogs, and personal home pages. Additionally, other genres such as information sharing sites, online forums, news article pages, and product description pages are also represented. The data is based on a 25% random sample of the benchmark, totaling 120 examples, which were manually annotated to determine their domain types. Figure 3 illustrates the performance of various models on our benchmark, broken down by fine-grained metrics. GPT-4v excels across all dimensions, with the exception of color where website VLM-8b leads. The use of text-augmented prompting significantly enhances block match and text similarity scores for both GPT-4v and Gemini Pro Vision. Self-revision prompting shows minor improvements in block match and position similarity for GPT-4v, but does not benefit Gemini Pro Vision. These results highlight the effectiveness of different prompting strategies and the strengths of GPT-4v in this task. In this chapter, the authors benchmark various models and methods, focusing on both prompting commercial API models and fine-tuning open-source models. For multimodal prompting, they develop direct, text-augmented, and self-revision prompting methods using GPT-4v and Gemini Pro Vision. In fine-tuning, they use CogAgent 18b as the base model and fine-tune it with the website dataset, employing LoRa for optimization. The evaluation includes both automatic metrics such as position, color, and clip, as well as human pairwise preference assessments. Table 2 presents the automatic evaluation results of various models on 4 fine-grained similarity measures and high-level visual similarity using CLIP. GPT-4v performs exceptionally well across all metrics, with the exception of color similarity where website VLM-8b takes the lead. Design2Code 18b, despite being fine-tuned on less data, demonstrates robust performance in block match and text similarity metrics. Figure 4 presents the results of human pairwise preference evaluations, using Gemini Pro Vision direct prompting as the baseline. The evaluation involves sampling 100 examples and having 5 annotators compare each pair of examples. The majority vote determined the outcome for each example, with higher win rates and lower lose rates indicating better quality, as judged by human annotators. In the automatic evaluation, GPT-4v performs the best across all dimensions except for color, where website VLM-8b leads. Text-augmented prompting successfully increases the block match and text similarity scores on GPT-4v and Gemini Pro Vision, showing the value of providing extracted text elements. Self-revision has minor improvements on block match and position similarity for GPT-4v, but no improvement on Gemini Pro Vision. In human evaluations, GPT-4v is substantially better than other baselines, with text-augmented prompting further improving performance. Self-revision prompting is not helpful for Gemini. There are interesting discrepancies between automatic and human evaluation results. For instance, human evaluation ranks GPT-4v self-revision prompting better than text-augmented prompting, while automatic metrics show mixed results. Position similarity and clip similarity are the most correlated automatic metrics with human preferences, suggesting that humans focus more on high-level visual effects and layout rather than detailed content. Table 3 presents the coefficients derived from logistic regression used to predict human annotations on the win/lose outcomes of model comparisons. The analysis reveals that human evaluation is significantly correlated with position and clip similarity metrics, indicating that these metrics capture aspects of web page quality that align closely with human judgment. In contrast, text similarity shows minimal correlation with human preferences, suggesting that detailed content may not be as critical to human assessment as high-level visual and layout elements. To understand what makes a web page difficult to generate, we analyze the correlation between automatic metrics and various difficulty indicators. The total number of tags in the reference implementation was found to be the strongest indicator, with more tags correlating to lower scores. We also examined the learning process of different automatic evaluation dimensions, finding that performance on block match, text, and position quickly stabilizes, while color and clip similarity steadily improve. Qualitative analysis showed that text-augmented prompting improves recall, self-revision prompting fixes missing elements, and website VLM-8b excels in coloring and layout but struggles with text matching. Table 4 illustrates the correlation between various automatic metrics and 3 proxy difficulty indicators for GPT-4v self-revision prompting. The analysis reveals that the total number of tags in a web page is the most significant indicator of difficulty, with web pages containing more tags generally being more challenging for the model. Specifically, metrics such as block match and position show significant correlations with difficulty, indicated by a p-value less than 0.05. Conversely, the DOM tree depth has a minimal correlation with the difficulty of generating the web page. This data suggests that while certain metrics are more sensitive to the complexity of the web page, others provide less insight into the model's performance challenges. Figure 5 illustrates the learning process across various automatic evaluation dimensions, showing the performance progression from the base model checkpoint to all training checkpoints. Each dimension score is normalized, starting at 0 before training and reaching 1 after 50-100 steps. The y-axis is adjusted to accentuate larger value differences. Notably, block match, text, and position dimensions reach saturation after 2,000 steps, indicating stable transferability from the base model. Conversely, color similarity and clip similarity continue to improve, suggesting that these aspects benefit more from extended HTML training data and could further enhance with full website dataset fine-tuning. Figure 6 illustrates an example where text-augmented prompting significantly improves over direct prompting. The output from direct prompting misses most of the text contents, whereas text-augmented prompting successfully recovers them. This improvement is quantified by an increase in the block match score from 0.25 to 0.84, demonstrating higher recall in the generated content. Figure 7 illustrates how self-revision prompting enhances text-augmented prompting. In the first example, self-revision recovers missing elements, boosting the block match score from 0.48 to 1.00 and clip similarity from 0.87 to 0.91. The second example demonstrates how self-revision corrects layout errors, elevating overall clip similarity from 0.85 to 0.91. In the realm of multimodal large language models, LLMs, Blip2 serves as a notable example by integrating Vision Transformer, VIT, with large language models through QFormer. Instruction tuning, as seen in models like LLVA and InstructBlip, enhances the model's ability to generalize to unseen tasks. Commercial models such as GPT-4v have shown promising results in adapting to various vision language tasks, including UI interactions. For UI code generation, Design2Code employs a combination of convolutional neural networks, CNNs, and recurrent neural networks, RNNs, while more recent approaches incorporate neural network-based object detection and advanced visual encoders like VIT. In the context of code LLMs and programming support tools, models like Codex and StarCoder have enabled a range of applications, including automatic code completion and infilling. These advancements have also spurred research into human-computer interaction, HCI, to improve human-AI collaboration in programming. Figure 8 presents a comparative analysis between Website VLM 8b and Design2Code 18b models. Website VLM 8b demonstrates superior performance in color recognition with a score of 0.99, significantly outperforming Design2Code 18b's score of 0.66. However, Website VLM 8b exhibits a tendency to hallucinate text contents, which impacts its overall accuracy in text-related tasks. This comparison highlights the strengths and weaknesses of each model in handling visual and textual elements within their respective domains. In this work, the authors introduced the Design2Code benchmark, which includes a variety of real-world webpage examples. They developed automatic metrics and conducted human evaluations to compare different multimodal code large language models, LLMs. The results showed that fine-tuned open-source models can perform similarly to prompting Gemini Pro Vision, but still fall short of GPT-4v. Human annotators found that 49% of GPT-4v's outputs were good enough to replace the original references, and 64% were judged to be even better designed than the originals. The authors believe Design2Code can be a valuable benchmark for future research, suggesting areas such as improving prompting techniques for complex web pages, training LLMs with real-world web page data, and extending the benchmark to include different input types like Figma frames or sketch designs. Thank you for watching.